Okay, at the end of the last video, I left a 0 out here inadvertently. Put a note in the document indicating that had happened, but here it's been corrected. Not as neatly as I'd like, but it's been corrected. Okay, now, using this function y equals 0.00019x squared, we plug these x values in, and the y values that we get are 106, 86, 69, 50, 27. They tend to run high, 5 to 10 units higher than these values. They have the right general trend. Of course, the last value here would be 0. And it probably wouldn't hurt to put that in, but that's kind of going to be automatic by the nature of the function. So it doesn't really give us any kind of a test. This process didn't come out with a completely accurate result, although if done correctly and done carefully, it would. Now, we're not so much interested in the ability to sketch this and make accurate estimates, although we do want to have that ability because it has all kinds of applications and it connects us in a way that we wouldn't otherwise connect to the process. But taking this information, constructing this curve, is a model for what we do when we actually fit this with the appropriate curve. And it turns out that the curve that's appropriate to this data is the y equals ax squared curve. Now, there are things that we can do with this where we can transform this function into a function that models our original data, and we're going to take a quick look at that. Okay, now, question I want to ask, we want to relate this model, which came from this table, to our original depth versus clock time data. How does this function model this data, or how is this function related to the function that models this data? Well, actually, the answer is fairly simple. Our x values were obtained, remember, by calculating the horizontal distance between a data point and the vertex, so that the vertex having x coordinate, or having clock time coordinate 810 seconds, the horizontal distance between the first data point and that vertex is 810 seconds minus 61 seconds. Okay, that's what this distance is. Here's 61, here's 810. So this 749 could have been calculated by 810 minus 61. And of course, that's 810 minus 61 seconds. Okay, this is in seconds. And similarly, 674, well, our point 136, 110 would be at 136 here, which would be a horizontal distance of 810 minus 136. So this is 810 minus 136, etc. So we can write over here, what we learned from there is that x is equal to the 810 seconds minus the clock time. So x is 810 seconds, and I'm going to suppress the seconds right now, but I'll reinsert them shortly. Okay, so the numerical value of x is 810 minus clock time, and 810 and all x values are in clock time in seconds, and all our clock times are in seconds, as indicated on these tables. Okay, what about our depths? How do we calculate our depths from these numbers? Well, we're calculating relative to the 30 millimeter depth at the vertex. So we're subtracting 30 millimeters from each of the depths. Okay, so that 130 minus 100 gave us the 30, and 110 minus the 30 gave us the 80. 90 minus 30 gave us 60, etc. So here's 130 minus 30. Here's 110 minus 30, etc. And we can easily see then that y equals the depth minus 30. And these are in millimeters, so y will be in millimeters as x will be in seconds. Now, why did we subtract clock time from 810 when we subtracted 30 from the depth? Why are we subtracting the time coordinate but subtracting from the depth coordinate? Because x and y were defined in terms of distance, and the distance from here to here is going to be 810 minus the coordinate, whereas the distance in the vertical direction, since all the vertical points are higher than the vertex, will be the coordinate minus the vertex. The coordinate minus the 30 millimeters at the vertex. So the 30's got to be subtracted in order to get a positive result for y, whereas it's the clock time has to be subtracted from 810 to get a positive result for x. And remember, the distance is always positive. And that's how these things were defined at the beginning of the problem. So x is 810 minus the clock time, y is the depth minus 30. Our model was y equals 0.00019 x squared. So how do we put all that together to express our model in terms of depth and clock time? You should give that some thought. The answer is really pretty obvious. You'll see it as soon as I write it down. Let's see if you can see it before I write it down. Okay, well, I'm going to write it down. Well, y is depth minus 30. So we replace y by depth minus 30, and that's going to equal 0.00019, get all those zeros in there like I did before, and that's going to be then times x squared, which is 810 minus clock time quantity squared. Well, that's good. That's good. So we want depth as a function of clock time now, because that's what we have here. So we simply solve this for depth, and we obtain depth equals what? Think it through yourself. And I'm going to write it down. Well, depth is going to equal 0.00019 times 810. Now I'm going to use T for clock time. We've been used to using Y for depth, but we can't do that because we used Y for something else, and we don't want to confuse ourselves. So we're going to do 810 minus T, and of course we have to have the square on there. And then what happens to this 30? Well, we solve for depth, so we're going to have to add 30 to both sides, and there's our model. Now, we could expand the square and get this in slightly different terms. So I'm going to do that off camera. I'm going to have to do a little work here. I'm going to have to square 810, which is about 640,000, interpolate 660,000 to the nearest 10,000. And then I got to multiply that by 0.00019. That's going to come out a little over 1,000. So yeah, let's see how it comes out. A little over 100, I guess. So I'm going to have to do some messy stuff here. So I'll do it off camera so you don't have to watch. Now here's what we get. But let's look here and see what the difference between this information and this information is. This information here clearly tells us where the vertex of the parabola that we get when we graph this function occurs. The 810 is right here. That's coordinate of the vertex. The 30 is right here. Okay? So we can just read this off if we know how to manipulate graphs, if we know the rules for transforming graphs, for shifting and stretching and so forth. So it's well worth knowing that. This is something everybody's seen if they've been through at least Algebra 1 and geometry. And it's worth relating back to what you know. Transformations of graphs, shifting and stretching. Okay? You should relate that to what you see here. But then I go ahead and expand this and collect terms, and I believe the model then is 0.00019t squared minus 0.31t plus 155. Okay? Either of these models is correct. This one actually contains more information than this one if you want to just read off the coordinates of the vertex and some other important characteristics of the graph. And you should also understand from what you've learned that if you complete the square on this, you get back to here. Okay? So this is obtained by just squaring this and multiplying stuff and collecting terms. Very straightforward. This would be obtained by completing the square. To come from this, you would complete the square to get this. That's a little more complicated, but it's just a mechanical procedure that isn't that difficult. Now, the main thing we want to do here is see how this model corresponds with our original data. So we can plug in these clock times into this function, either this form or this form. It doesn't matter. I'm going to go ahead and use this form to make sure I did it right all the way through, and see if our depths come out consistent. What actually should happen is that the depths that we get should be the same as the depths that we got over here if we transformed this function into these coordinates. Okay, now I plugged 61, 136, etc. in for t, evaluated this expression, and I got these results. Now, these numbers aren't the same as these numbers, but remember that these numbers should be 30 less than these numbers. If you subtract 30 from each of these, you will get the numbers that we have here. Now, I did a little rounding off when I wrote some of this stuff down, and I wasn't absolutely sure that these would come out would round off to exactly the same numbers, but it turned out that they do. If we just subtract 30 from each of these numbers in green, we get the numbers in red, and you should understand why that's the case. Now, I'll mention that this is a quadratic function, and you should review or anticipate how you graph quadratic functions. You complete the square, you identify the vertex, etc. I'll observe also that the a y equals ax squared function is also a quadratic function, and when any quadratic function can be put into this form by a suitable set of transformations. This form is the form of the four-plane graph, and that means that if you have quadratic data and can determine where the vertex is, you can translate that data into this format, and it will be a y equals ax squared situation, okay? If you do indeed have quadratic data. If you have any parabola, you can do this. You can do the same thing we've done here and model it with ax squared, and then transform it back into whatever this is versus whatever this is. Sorry, whatever this is versus whatever this is.